Most wars are fought over resources: water, oil, minerals.
China has a near monopoly on global critical minerals production. As America struggles to rebuild these industrial capabilities domestically, chemist and nanotechnologist Dr. James Tour at Rice University has found an ingenious solution.
We can pull out one metal, and then the next, and the next, and the next.
He's pioneered a process to quickly extract critical minerals from something we have readily available: electronic waste.
It's much cleaner and much faster.
The same method can be used to extract rare earths from mine tailings, the leftover material of old mines that was too expensive to process in the past.
There's huge availability of this, and if you recycle it, metals are infinitely recyclable. This will solve the problem. Now, it won't solve it overnight because we have to gear up, but it could solve the whole problem within 5 years.
This is American Thought Leaders, and I'm Yanya Kellick. Jim Tour, such a pleasure to have you on American Thought Leaders.
Thank you for having me.
So recently, the Chinese Communist Party basically put unprecedented export controls on rare earths, frankly affecting the whole Western world. There was a deal reached. There seems to be some backtracking since. What were you thinking when you saw this?
Well, it's not just rare earths. It's a number of other metals too. They're now calling them critical metals. So it's copper, it's indium, gallium, tantalum, antimony, and several others. We turned over manufacturing to them over the last 30 years, and so we have very little capability to manufacture these metals in the U.S. And a lot of times, if they're mined here, they'll go to China for processing. So we don't have the capability to take the ores and to turn them into the base metals that we can use. It's a big problem, and we wouldn't be able to build electric vehicles here. We wouldn't. This would shut down our manufacturing of our automobiles. It's over. This would shut down our Intel plants, our chip manufacturing. So it's a very big deal. And even just the threat of it shakes up the markets.
And now you're working on technology that's directly related to this issue.
Yes.
Yeah, so explain that to me.
We developed a technology in my group called flash joule heating. And it's not a name that we coined, that's been around, where you put a high voltage and a high current through a material that is not highly conductive, has about a 1 ohm resistance, which means that you can conduct electricity through it. It's much like your toaster. Your toaster, you have this coil that you put a voltage across it and you run this current through, but there's enough resistance that coil gets red hot very quickly. That's flash joule heating. And it's like the old incandescent light bulbs, and you see this big glow. And what we learned is that we can put any carbon material between electrodes and flash joule heat it, turn it into graphene. Graphene is the space-age material, and we started a company around that. That's up and going. But then we realized that we could take certain materials, say industrial waste, like fly ash, which is the residue that's left over after burning coal, the inorganic material. We could flash it, and we could get rare earth elements to come out. And so we could do that. We could get other metals from industrial waste, and then also consumer waste, consumer electronics, and you can put a high voltage, high current. And then we learned if you put chlorine in during the process, then they come out much more easily because you convert them from metal zero or metal oxides to metal chlorides, which are much more volatile. You lower the boiling point by 3,000 degrees, and then they'll come out. And just based on the reactivity of a certain metal to chlorine at these higher temperatures, we can predict when they're going to come out, and we can separate them coming out. So we developed this technology. We started doing this in 2020. We started doing this on metals. And then it was after that the metals, that China put this kibosh on sending us metals, and it became a much more important. So I found myself in this very important area.
Okay, so let me get this straight. You're taking electronic waste or tailings or something like this. You're putting them between two plates. You're putting a massive amount of current through it. Wait, you're adding chlorine to lower the temperature that you to get them this red hot, to separate everything out. And then you're somehow collecting each metal chloride as it basically distills out. Do I understand it right?
You have it right. So what happens is when the chlorine comes in at these high temperatures, the chlorine will react with the metal oxides or the metal zero. By metal zero, I mean the base metal. You can have a metal oxide or a base metal. And it will make the metal chloride. And then the metal chlorides distill out. And the thing we control is at what temperature are we heating this to react with the chlorine, and then at what temperature are we distilling it out. And based on those two parameters, we can pull out one metal, and then the next, and the next, and the next. So that's right. It's really that simple. It's a very simple operation. As you know, most wars are fought over resources: water, oil, minerals. People fight over this, and they kill each other over this. So when I was presenting this to a group of generals from NATO, and the head guy there, he stood up, he says, "This is going to prevent wars." He says, I don't have to fight for this now. If you can do this, if you can take our waste and be producing this for us, I don't have to fight wars over this. And we can set up these factories. So the first factory is like $40 million, but it's cheaper the next factory we build because we've worked out all the technology. And so if we can put these together, and they're small localized factories that are not generating a bunch of waste. China has absolutely contaminated some of their cities. I mean, it's just toxic to live there because of the waste that normally comes from some of these processes. Now, you don't have to run them that way. You can run a hydrometallurgical process and be quite clean, but you have to be able to trap all these secondary wastes. These are clean, easy to set up, and that's why we're building these companies. The first one is just outside of Houston in Texas. The next one, we have a site, pre-permitted site in Massachusetts, another one in Virginia, because these are very clean. And we've been asked by the federal government to set up more of these entities around the country. And think about this, to be able to not be dependent upon other countries. Look at our president. He's going from place to place, setting up deals on rare earth elements. Here he's talking with Ukraine to say, hey, we'll move in there with you, and that will help prevent future wars. I mean, this is dangerous stuff, and it's expensive. And but if we don't have to do this, this is a win-win all around.
It's sort of astonishing. I've been learning a bit about this particular process, and big question, first of all, is when you think of these let's say circuit boards, right? This is an example of the type of waste that you're using, right? There's a lot of this stuff out there. I mean, we're shipping some of it, as I understand, to Africa to basically waste to landfill it. I don't even know what they're doing over there with it.
So we take this waste, electronic waste, a lot of it we just ship to Africa, and they will go through a number of processes to try to reclaim that metal. It's never. In many times it wasn't worthwhile to us to try to do this. They will take it apart and do this. But things have changed, and now there's more money in it. And so there's a number of companies, but we have, for example, printed circuit boards. I'm not going to individual houses saying, would you give me your old cell phones? These data centers, every time you store something to the cloud, that is going to a data center. That is storing in some flash drive on some chip somewhere on a printed circuit board. And they will retire these every 1 to 3 years. So you have a huge number of these things that are made by many different manufacturers. And so there's mountains of these, and these are considered a toxic waste, not by me, just by the government, because there's a lot of metals, and you can't just throw this in the trash. You can't just easily landfill it. And so there's huge availability of this, and if you recycle it, metals are infinitely recyclable. So you can recycle it again, and it's just a matter of the traditional ways of purifying this were really messy. You needed a lot of acid, a lot of water, And you generated what was called secondary waste streams from all of this processing. And the pyrometallurgical methods of just melting it all down wasn't able to pull these individual metals out as well. And so our method turned out to be quite fruitful, much cleaner, and much cheaper.
Okay, so wait a sec. Cleaner, cheaper.
Yeah.
What kind of numbers are we talking about here?
Well, when we always crunch the numbers now for any of the papers we publish, we have to do what's called a life cycle assessment and a techno-economic analysis. So we have to look at greenhouse gas emissions, which is mainly CO2 emissions. We have to look at water usage, acid usage, chemical usage, and we have to look at it from the cradle to the gate to where we sell it, or the cradle to grave where it's ultimately going to be disposed of again. What's the cost of this entire process? And so we have to look at all of these parameters, and the numbers that we get, we can often have less than 50% the amount of CO2 emission, sometimes just 10% the amount of CO2 emissions. Our costs are significantly less, many times 80% less, sometimes 50% less, and then if we take into account this is where we really win. If we take into account the shipping costs. So when something, say, is mined in Australia, Australia doesn't process anything. This is a mining country. Then it is shipped, put on barges, goes to China, where it's processed, and then from China it's shipped to places like the United States. So they'll take the raw ore, which is just metal oxides, and they'll convert it to the base metals, all separate, and then those come on barges to the U.S. So look at all that's involved in the shipping. If we could just have it right here in the United States, we don't have any of that shipping charge. And a mining operation is huge. Just the capex in a new mining operation is $200 million. $200 million. We could set up one of our factories for processing this material somewhere in the order of about $40 million. So 5x difference. Based on that, we don't have that huge amount of shipping costs all over the world, moving things back and forth. And we don't have the shipping cost of sending these off to Africa when we're done. So if we're looking at to the grave site, we save all of that. So overall, it's a very competitive business.
Jim, one quick sec. We're going to take a quick break, and folks, we're going to be right back. And we're back with Jim Tour, Professor of Materials Science and Chemistry at Rice University. I understand it's something like 75% of these circuit boards are actually still in the consumer level at homes and so forth. Is that right?
Yes. So that's always a problem when it comes to waste. How do you get it? Now, the nice thing about the printed circuit boards from the data centers, there are mountains of this that they have. But the things that are in households, that's always hard to get. That's what makes the recycling of plastic very difficult. People have to throw their plastic away, and then they're hand sorted and things like that. It's a difficult thing. And plastics that have been recycled are never as good as the base plastic because a lot of these polymer chains break. Whereas with metals, you don't have that. Metal goes to metal. They're infinitely recyclable. They don't go bad, but it's accumulating. How do you get these things? But there are other sources that you're not dependent upon that. So there's things called tailings, where there's been mining operations, and there were things that just weren't pure enough for them to go the next step. They had other impurities. They have huge ponds full of these things that are a nightmare for them because they have to maintain these ponds that have a plastic lining to make sure they don't leach into the water system, or they're stacked up in piles and accumulated. Those are just sitting there. That to us is a treasure because we can take those, bring them through this flashing process, and bring them up from 20% purity, which might be unusable to them, to 95% purity in an instant. I mean, it takes us seconds to bring it up that high, and we use very little water, and our only cost is electricity, but overall our electricity is much lower than the traditional processes because we're so fast. We use a lot of electricity for a very short time, and overall our electricity usage is small.
Let me understand this, though. So it's the same technology that you're using for the tailings and for this waste that you're going to recycle from the consumer waste and from the data centers. I mean, is it still the same technology for just actual ore?
It's the same technology for the actual ore. The problem with ores is they can be 1,000 times lower concentration of the metals than what I can get in an electronic waste, in a consumer waste. And so I have to flash 1,000 times more volume of material in order to get the same amount of metal. It is much more profitable for us to not work off of ores. And the ores come from some mining operation where they've spent a lot, huge capital equipment to do mining and then transporting it here. If that mine is outside the United States, again, all this shipping charge. And then it's a volume problem. I'd much rather work off of electronic waste where you might have a printed circuit board could be 25% metal, whereas an ore might be 1% metal. So it's just a big difference, or less than 1% metal. So it's much better. And so from an environmental standpoint, it's much better. From an energy standpoint, it's much better. And if we can just think about using our waste and recycling it, it's a good story all around.
So the electronic waste is 1,000 times more concentrated with these metals that we want compared to regular ore. What about the tailings?
The tailings can be quite high. It's not as good as the electronic waste that I can get from a printed circuit board, but the tailings have already been pre-purified from the ores. So they've taken the ores and they've concentrated it, and they have something that's just not high enough for them to bring on the next step. They'd like to use it, but there's too much other things in there, but it's still a pre-concentrate.
So what's the catch here? I mean, it seems like this is the perfect solution to actually, getting the U.S. up and running in terms of production of these metals.
The catch here is that nobody's ever done a process like this before. So we had to go from my laboratory where we'd start on 50 milligrams, and then we bring it up to 2 or 3 grams, and then it has to go to where they're going to be processing many tons a day. 20 tons a day is what the projection is so they'll start with a ton a day in January of 2026, and by September, October, they hope to be 20 tons a day of printed circuit boards, where they would get some portion of that, maybe 2 tons per day to 4 tons per day of metals out of that. So the catch is, how do you scale this? So we spent 2 years working with engineering companies to be able to scale up this process. And that was actually, if you look at it, it was actually more than 2 years, because on the graphene side, when we were making graphene, we spent from 2019 until 2025 before we hit the 1 ton a day mark. So we learned a lot doing that. Then when we started the metal separation company, it took another 2 years for the chlorine introduction part and the separating of the metals from that, because it's not exactly the same technology. It's related to the graphene, but so it had to be developed. All of this had to be discovered.
The one thing that strikes me here is that, this is also something that Americans could actually be rallied around, because there is a lot of this electronic waste at home, for example, right? And I think this, these export controls which the Chinese Communist Party threatened America and frankly the entire West with were a crystallizing moment. At least I hope that they were a crystallizing moment. So I wonder if this doesn't even have a kind of a patriotic dent in it to it, or an element to it.
Yes, if you could tell people that if you take your electronics that you're getting rid of and you put them in a certain container to be carted off, this is patriotic, I mean, that would be a further incentive for people to do it. So these things are there, but also what we're getting from the Trump administration is we're getting a guaranteed floor price. So they're saying, we will pay you X amount for your rare earth elements, because what will happen is this is the way some countries operate. So they don't like us developing this business. They will artificially lower their price in a way that we could never compete and drive us out of business. As soon as we're out of business, they will raise the price back up. So what the U.S. government is already doing, preemptively saying, we will guarantee you this price. And it's not really the U.S. government supplementing it. That's the price that it's going to ultimately be sold for. And so by doing this, they will allow us to get this start, that we won't be driven out of business. So we're getting actually a lot of help and consideration from the U.S. government to say, hey, we really have to do this. So this is an important thing for the country. And we offshored so much of our manufacturing. We're trying to reshore a lot of that, and because we see what can happen. And President Trump went and he recently, as you know, made a deal, and China said, okay, we'll start selling this to you again. You know, I wonder how much of that was just out of the goodness of their hearts, or because they saw these other technologies coming online. Because when you make it difficult for somebody to get something, they will figure out another way. It always happens. I saw it happen in oil and gas industry with guar for fracking. The Indians kept raising the price, and then boom, they came out to something called slick water, which you add polyacrylamide, a chemical, so you pump at a fast rate. You find a way around. But interestingly, after President Trump left, a couple weeks later, they say, yeah, we will sell it to the U.S., but it can't go into any of your military hardware. So again, we have to have our own capability. We can't be held to the whims of other people around this. And that technology that the Chinese are using, that was developed in the U.S., actually. It was developed in the U.S. during the Manhattan Project because we had to get because when you get uranium, you get rare earth elements with it. We had to separate the rare earth elements to get the uranium, so we figured out how to do all of this separation. That technology was purchased by China. Actually, it started to get purchased in the 60s, again, heavily in the 1980s, because the U.S. was getting out of the business, because in the rare earth element business, you were pulling up uranium with it. Now we want the rare earth elements. We didn't need the uranium. And that was for us a radioactive waste, which is very expensive to get rid of. And so the Chinese bought the technology. And again, we didn't realize that we were selling something that turned out to be very important to our country.
Well, Jim Tour, it's such a pleasure to have had you on.
Thank you.
Thank you all for joining Jim Tour and me on this episode of American Thought Leaders. I'm your host, Jan Jekielek.